Okay, guys. We went through loose dot structure, and we took a very simple ones. And one of the very important stuff about loose dot structure, you have to know electronegativity. What is electronegativity? And then we'll go for the one that we did not finish last time, that difficult one. But before that, let's look at the electronegativity here. This is the table of electronegativity with fluorine atom being the highest. This is the highest, and it has no units, has 4.0. So fluorine is the highest. And cesium and francium here, the lowest, and their electronegativity scale is 0.7. So therefore, electronegativity is opposite of electropositivity. We have two, terms, electropositivity and electronegativity, but we are interested in electronegativity. It turns out electronegativity is the ability of an atom to attract VEs, valence electrons, from adjacent atoms within the chemical compound. It has to be what? Within the chemical compound. Okay, guys, so this is the definition. Okay, everybody is following me here. The definition of electronegativity is really a scale. There's no units for it. That's just a scale. Scale is the ability of an atom to attract valence electrons from adjacent atoms within a chemical compound. So we have the highest one that good ability to attract those valence, to pull out those electrons towards itself. So to attract means to pull in these VEs towards itself. So let me tell you a scientific. Well, you can consider it a joke, but it's not really a joke. That's a real. And I'm not liable, so there is no liability. Don't do it at home, okay? So let's look at this. There's a feud between between spouses here. Maybe about life insurance, whatever. And one wants to make some harm to the other. Okay, everybody's following? So, and the other one has a little bit, or the husband or the wife, I don't know. This is just one of them has a little bit knowledge of chemistry and about electronegativity, correct? So he took about 1,000 toothpaste, put them in a big container, 1,500, 600, large amount of toothpaste, empty them in a container, and then boil them very slow under very weak flame or very weak temperatures, not higher temperature, very lower, the lowest temperatures for a long time. So he wants to concentrate this toothpaste. Then took one of the empty containers, so suppose he or she has 1,000, so two containers of the teeth paste, put it in one of those containers and put it back in the shelf. So the next day, one of the spouses came in and wants to brush his or her teeth. As soon as that person came and brushed her or his teeth, tooth after tooth is going down. So the whole teeth are, and that person looked like 100-something years old, correct? and you cannot speak even very well because all the teeth are out. What's happened? What inside the toothpaste had caused that person to lose all the teeth? Somebody will tell me? Come on. The answer inside this? The answer inside this. It has what? Calcium fluoride, correct? It has the tooth or teeth paste. They do have calcium fluoride to kill what? The bacteria. It's the same token, the same idea. We add calcium fluoride inside the toothpaste to pull out, because fluoride is so aggressive, it will pull out the valence electrons of the bacteria. So pull out all the valence towards itself, the bacteria is killed, correct? Pull out, because the bacteria is like human. We are made of nitrogen, we are made of carbon, we are made of a lot of elements, covalent, non-metal elements, that's easily can be taken by most electronegative. Fluorine, the fluoride ion or the fluorine atom has the highest affinity towards valence electrons. Anything a valence electron wants to take it in, therefore it's the highest scale, 4.0, correct? Now, that person came and brushed the teeth without knowledge that's calcium fluoride, which has to be very, very minimum. Does not realize that's about 500 or 1,000 toothpaste had concentrated calcium fluoride to non-acceptable concentration. And then as soon as that person had started to brush the teeth, calcium fluoride will come and take all the valence electrons of the gum. All valence electrons in the gum are pulled out by calcium, the same thing with the bacteria. So all the teeth are down at the same time. Are you following me? But I'm not liable here. I'm saying I'm not liable. Don't do it to anyone at home. Don't do it. No, I'm serious. Don't do it. But that's really true. So if I have in the toothpaste higher concentration of calcium fluoride, I'm not killing in the bacteria. I'm killing my teeth too. The teeth will be gone. Are you following me here? And that's the reason inside the labs, we don't put calcium fluoride in glass, in bottles of glass. We cannot afford that. It will start eating the glass. And after a while, the glass will be like a mashed potato looking. It will be dissolved, like it will eat up the, and if you look at the burn, depending on concentration of the compounds of fluorine atom, it can cause up to the 3rd degree burn. So it's very dangerous. If it's dilute, maybe 1st degree, 2nd degree, but if it's in higher concentration, can cause very, very bad damage to the skin, to that person. And if it's swallowed with higher concentration, that's deadly anyway. So it will pull out all electrons from the stomach, from the throat, from the tongue, from all the organs inside the body. So you get the idea what electronegativity means? Electronegativity is the ability of an atom that's very unique for fluorine with the highest scale. Anytime you put fluorine as an ion or as a molecular fluorine gas near adjacent within the compound itself, so it will come and then within the compound. Fluorine gas might not be, will be very, very aggressive too, but it's not like within the compound. Within the compound, it destroys the compound, start to pull out valence electron from whatever its neighborhood. Are you following me here? So that's what we mean by electronegativity. And it turns out the electronegativity trend is the opposite of ionic radius. Electronegativity goes, electronegativity goes from, let me just change the color. So luckily today is not Monday, everybody is awake, correct? I hope so. I hope so. So from left to the right, that's within the period. That's a period here. So it says that the electronegativity increases. Of course it will increase because fluorine is here and lithium is here. Lithium is electronegativity scale is 1, while fluorine is 4.0. So it increases from left to right. However, This trend is the opposite of the, again, is always opposite of the atomic radius. So from, this is the bottom here, within the period, it increases from left to right. This is the period. Within the group, from top, that's the group here. From the group, you will see it will decrease, the opposite. The ionic radius, the opposite. Atomic radius will increase from the top to the bottom. And atomic radius within the period from left to right will decrease, while electronegativity is the opposite, will increase within the period from left to right and will decrease from the top to the bottom within a group. So you get the idea? It is very important to understand this because that's very, very important. Whenever you are dealing with the fluoride, you have to be really very, very careful, very aggressive, very, very aggressive. Any question about this? Any question about this? We'll go back and look at the values. Yes. From the top to the bottom is decrease. From the top to the bottom, decrease. What's that? The electronegativity, delta En, difference in electronegativity or electronegativity decrease, correct? And it increases from left to right. The atomic radius is quite the opposite. Within the period, from left to right, electronegativity increases. The atomic radius decreases. Atomic radius from top to the bottom will increase, but electronegativity will decrease. Correct? Now, we'll come back to this and you tell me which one we'll put in the middle of the Lewis dot structure, which one we'll put at the edge. So, can I take this one out? Take this one out? Okay. Now, we'll come back to this. Let me just put this one here and have one without table here. So I have, remember last time we did not finish it, but I said we'll come back to it. I put for you PO, phosphorus, oxygen, and chlorine. So if you look at the period, if you look at the electronegativity of each, and you can verify it here in general, where we have it here. So phosphorus, where is phosphorus? Phosphorus is 2.0. That's a scale, no units, correct? Oxygen is the second highest, 3.5. And chlorine, third highest, almost like nitrogen, 3.0. So my intuition will tell me when I start, let me just take this one out. So the least in Lewis dot structure will start, except when I have hydrogen. I'm forced, if I have hydrogen, to keep hydrogen at the edge because hydrogen has only one electron. But here, my intuition will tell me which one I have to put in the middle. The least, what? Electronegative atoms, correct? So I put the phosphorus is here. And the oxygen and chlorine, those most electronegative, the difference between them is 0.5. I cannot put them very close to each other. I'll try to get them. Here's the oxygen, here is chlorine, here's chlorine, and here is chlorine. So I'm trying, let me just take this one out, maybe make the phosphorus smaller so we have space to, so phosphorus is here. Then I have to put the valence electron of each. So you tell me what is the valence electrons of chlorine? What is the valence electrons of chlorine atom? Chlorine atom in what group? 7A. You have to know this, not by heart, but at least you get the idea. The 7A always minus 10. 17 minus 10 is 7. That's 7A. Group oxygen, 16 minus 10, that's 6, 6A. Correct? 18, noble gas, helium, neon, argon, krypton, xenon, radon. So this one here, 18 minus 10 is 8A. Are everybody's following? Always minus 10. It start from 13, correct? Start from 13, and even from the other ones, always, when it come after 10, you have to switch minus to minus 10. So, chlorine is 7A, so it will have how many? 7. Let's put this one here a little bit. It will have 7. Those are 7? Yes, those are 7. And this one here. How many is oxygen? Oxygen, guys? How many? 6, correct. Luckily, we are not in Monday. Okay, that's good. Okay, so how many phosphorus? How many? 5. 15 minus 10 is 5. So this is 2, 3, 4. I put the 5 here. So I start now connecting covalent single bond. First, you start with what? Single bond. So I connect, this is a bond, this is a bond, this is a bond, this is a bond. Which one of these elements I have to observe the octet rule for it? Well, the octet rule I have to observe for those 4 elements only. I don't care about the other elements. Those, they have to have octet, 8 electrons combined. So, but this one here, oxygen, the only one inside, correct? So I have 1, 2, 3, 4, 5, 6, this one 6, 7. Well, you will do everything possible to get oxygen and carbon and nitrogen and fluorine 8. So what I will do here, I will do maneuvering here a little bit. So I will take this one here, put it here. Creating the single bond does not do it, let's try making double bond. If the double bond does not do it, let's do it triple bond. So I'm moving this one here out, correct? So take this one out and move it to this place here, correct? So then I have here double bond. Let's see oxygen. I have 2 sets of unpaired, lone pair. So those are called, all those called here, all those by themselves, they have specific name for them. See, they are called unpaired, BEs, or non-bonding. BEs, or it's not used in the books, but you can tell them without parents. Those are orphans, orphan BEs. Meaning what? They are by themselves. They are not associating themselves in a family, in a single or double or triple bond. They are shared. So single bond are shared with both elements, but if they are staying in a space like this by themselves, they are called unpaired electrons, valence electrons, or non-bonding valence electrons, or orphan valence electrons. So now we have the structure of this. Let's look at Oxygen is the only one we have to consider the octet rule. Let's count this one here. Let's count. I'm counting this one here. 1, this one here. 1, 2, 3, 4, 5, 6, 7, and 8. So octet rule is okay. So oxygen has an octet. So this is the Lewis dot structure of this molecule. Why we have to put phosphorus? That's the rule. The least, except if they have some exception for the rule. I'll show you in a minute. So, any question about this? Any question about this? Can I take it out? Take it out? Okay, let's take it out. So I'll take it out and then rewrite this molecule in the way you can follow me. So this molecule will be looking like this. This is the Lewis structure of this compound. Is this following? Okay, so let's look at the ones that have charges. One has positive charge or one has negative charge. So we have to count first. I did not tell you. We have to count the valence electrons to make sure that we have this is really correct. That's double check. So phosphorus, we say 5 VEs. Chlorine is multiplied by 3 chlorine, 3 multiplied by 7, 21 VEs, correct? And oxygen, 1 oxygen is 6 VEs. So what's the total here? 21, 6, and 5. How much they are? 21 and 5, that's 26, correct? 26 and 6, how much? Total are what? Total VEs involved are 32. So we using this total valence electron, just double check that ours are correct. Let's count them just for this example. 1, 2, 3, 4, 5, 6. This is 6 here. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. This is correct. You can say with confidence, 100% assurance that this is the correct Lewis dot structure. All the valence electrons are accounted for. None of them is missing. None of them is missing. Okay? Any question about this? Any question? Okay, let's take ones. They have charges. We'll take 2 of them here. And by the way, whoever is with me today, we have Whisper, which we'll go through this again. You'll hear this one again in the lab. Monday's lab we'll hear this again in Monday, but today's lab, Wednesday's lab, we'll hear that again. So here it is. Let's look at. We want to see how about if I have ammonium. If I have a positive charge, it means what? You have lost what? 1 electron. Positive charge means this is called ammonium ion. Ammonium ion is a cation, correct? It's positive. It's a cation or ammonium ion. Had lost 1 nitrogen. So total VEs, how much total VEs we are dealing with? Total VEs, 1 nitrogen and 4 hydrogen, correct? So one nitrogen, what's the VEs of nitrogen? 1 multiplied by, what's nitrogen in? 5, 5. Okay. Hydrogen is 1A, 4 multiplied by 1 is 4. This is odd number, 9. But we have the charge, we have charge, one charge, because this is one positive, correct? One positive, understood, not written. One charge lost, so it will be 9 minus 1. Total of electrons are what? 8 VEs total. So hydrogen is always at the edge. So regardless, I know nitrogen is 3.0 or something, 3.0, and hydrogen is 2.1 in electronegativity, but I have no other choice. Hydrogen has the priority. Hydrogen has to have at the edge, cannot be in the middle, cannot be in the middle. So nitrogen has 5, but we have one here, hydrogen, one here, hydrogen, one here, hydrogen. So I'm connecting those together here. 1, 1, 1. Correct? And then I have 4 of them, correct? I have 4 of them. So let's put here. And here 1. So let's put this one here like this. So this is NH4. And then I put the whole thing here because this is missing, see here? Nitrogen is missing 1 electron, correct? Nitrogen is missing what? So I will say nitrogen has how many VEs? 5. 5 VEs of nitrogen. But present is 4. Present 4. 5 minus 4 plus 1. And this plus 1 here will appear as a charge. Correct, guys? Everybody's following? So let's do another one. Let's do the carbonate. And we'll do even the nitrate. So let's do carbonate and nitrate. And that will be good. Then we'll go for whisper. Can I take this one out? Everybody has it? Everybody has it? Okay. Okay. So let's take this one out. And let's look at another example. Let's look at another example. So how about if I have CO3 2 minus? Now I have a negative charges, means this one is not losing. Losing is positive, correct? Because you lose a valence electron, you lose negative charge, then the molecule will be appearing positive. But you have 2 negative means gaining what? 2 VEs. So the negative means when you have a negative that you are gaining more negative VEs, correct? So as you can see, oxygen is 3.5, and carbon, we can go back and look at carbon. Carbon, how much has carbon? 2.5. Can you see it? 2.5 here. Can you see the 2.5? So which one will be at the central atom? Which one will be the central atom? Carbon. Always in general will be the least one. So carbon will be here. One oxygen is here. One oxygen is here. One oxygen here. You will never do this carbon, oxygen, oxygen, oxygen like this. Nature will not support this. Why? Somebody will tell me why? Well, those are, oxygen is the second after fluorine, electronegative. They start fighting each other. They start pulling its valence electrons towards itself. This one start pulling, and the whole molecule is not stable. It does not exist because it fights itself. And I'll show you another one, the same idea. So try whenever you have an electronegative atom like fluorine and oxygen, tries to spread them out through the molecule, so they will not come close to each other. Otherwise, they will fight themselves, uh, and the molecule is not existent. So, and most of those compounds that they have, by the way, so just for your knowledge here, they are highly explosive. Whenever you have those valence electrons near each other, they are not stable, correct? And they can just explode in any time, correct? They are not stable. So let's look oxygen, how many? 6. So 2, 2, 1, 1. Carbon has 4, 1, 1, 1, 1. Oxygen 6, 6, 6, 1, 1, 1, 1, 1, 1, 1 here, 1 here. Okay, guys? Well, remember we did not add this yet. So I'm adding this one here, okay? Add this one here. Those are the negative charges. Those are the negative charges. Okay, guys? So those are the 2 valence electrons added to the molecule. Now, let's do single bond first. We'll start single bond. Remember, those are both are CNOF. Carbon, nitrogen, CNOF, oxygen and fluorine. They have an octet. They have to have 8. The total surrounding, bonding, non-bonding, they have to be 8. So I'll make first the single bond here, and single bond here, and see the octet rule. Well, it looks like carbon has 7. Carbon has 7. 1, 2, 3, 4, 5, 6, 7. No octet rule. That's bad, correct? How about here for this oxygen? 1, 2, 3, 4, 5, 6, 7, 8. This one is good. Octet. This one has octet. How about this one here? This oxygen? 1, 2, 3, 4, 5, 6, 7, 8. This one is good too. Octet. How about this one here? 1, 2, 3, 4, 5, 6, 7. This is not good. So this oxygen here and the carbon has a problem. So what I will do, same thing I did before. So I will take this one here, electron, move it to make a double bond, make it here, correct? And move this one here of a carbon, make it here. So I'm taking those here together. Then I have here 1 and here 1, and making what? A double bond here. Let's look now at this oxygen. Let's take the numbering of oxygen here out, and let's start counting them used with the double bond. What will happen? Okay, take this 2 here out. Okay, so let's look at this. It's a double bond here, and this is. So let's look at this. Now let's count. Let's count with different color. 1, 2, 3, 4. 2 sets of unpaired electron, non-bonding electron. 2 sets, and 2 sets of paired bonding. So this is called bonding, VEs, and those are called non-bonding VEs, or sometimes called lone pair by themselves, lone or orphan pairs. Okay, so we have, let's count them again. We have here 1, 2, 3, 4, 5, 6, 7, 8. So this option is good. How about carbon? We took this one out, correct? So we have for carbon 1, 2, 1, 2 carbon, 3, 4, 5, 6, 7, 8. So the molecule will be looking, if you allow me, everybody has it, I'll rewrite it again. Everybody has this? So it will be looking like this. Carbon has a double bond with oxygen. The oxygen, 2 lone pairs, or non-bonding pairs, or orphan pairs, and we have the other ones, single bonded, and then it has gained what? So now, what's the charge? Look at the charge here, guys. Brown here. So if I look at the charge of each element, what's the VEs of this? First, the VE of the element. VE of the element minus actual VEs. Thus, I can determine the charge on the element. Charge on element. Okay, guys, let's look. I have the VEs of oxygen 6, correct? That's the VEs from periodic table. But how about the actual one? The VEs on the oxygen. Well, 1, 2, 3, 4, 5, 6. 6 minus 6, 0. So oxygen has no charge on it, correct? How about carbon? 1, 2, 3, 4. So sometimes I tell the students to do this. Take a box. That's a valence electron. Take a box for oxygen, take a box for this, and take a box for this, correct? And okay, guys, so there is no charge on oxygen, so this is 0. How about carbon? Carbon is the actual one, not the actual, the periodic table is 4. This is periodic table. VEs. Minus, how many on it? How many on it? 1, 2, 4. 4 minus 4 is 0. So this one has 0 charge. This one has 0 charge. How about this one here and this? Let's try. What's the VEs of oxygen? 6. How many of it on it? 1, 2, 3, 4, 5, 6, and here 7. 6 minus 7 is what? Minus 1. So oxygen, this oxygen is minus 1 charge. How about this one here? 1, 2, 3, 4, 5, 6, 7, correct? 1, 2, 3, 4, 5, 6, 7. Yeah, 7, correct? So the valence electron 6 minus 7 is what? Minus 1. 6 is the from periodic table, and the actual one on it is minus 7. 6 minus 7 is this one again is minus 1. Okay, guys? So if I want to I will write it again. Can I write it again? Yes, I can. So everybody has it? Everybody has this? Everybody has this? Let's look at this. Can I take it out? Okay, let's take it out and look again. How does it look like? So I have here oxygen, and here oxygen, and one came out as this molecule gained two extra electrons. So therefore, I can write this one here. So this 0, 0, you don't have to write 0, 0. This is -1. This is -1, and the top of it 2 minus. Okay, guys, 2 what? 2 minus. Is this following? So this is carbonate anion. This is what? Carbonate anion. So let's take another one. Okay, guys, we don't write the zeros. You don't need to write. Just write the one that has charge of them. So let's take this one out. Already has it. Already has it. Let's take hydrogen peroxide. That's what I want to show you. H2O2. Where hydrogen has to be the edge, regardless. So hydrogen here, always at the edges. The two oxygen, we are forced to put them like this. They have 6, so 2, 2, 2, 2, 1 here, 1 here. 1, 2, 2, 2, 2, 1 here. And hydrogen is 1, hydrogen is 1. So we have, this is single bond here, this is single bond here, this is single bond here. And you can count for oxygen is 8. You can tell that's 8. 2 orphans, 2 lone pairs, set 4, and 4 and 2 single bonds, bonding 2 bonding ones. That's 4 plus 4 is 8. You know how to count those for oxygen, guys? Everybody knows? 1, 2, 3, 4, 5, 6, 7, 8. For the other one, the same thing. 1, 2, 3, 4, 5, 6, 7, 8. Okay, guys, so now what you can expect about this, what we have talked a couple minutes ago. Those are very electronegative atoms. Each one is 3.5. So this one is, I think, is about 2.0 or something. What's the, let me see. Hydrogen is 2.1. Yeah, 2.0, 2.1. That's bad. So, yeah, so 2.1. And oxygen is 3.5. And this is 3.5. And this 2.1. And this 2.1. Is this stable molecule? No. No. Why? Because you are putting two electronegative, second large electronegative after fluorine together. They'll start what? Fighting each other. I mean, they will pull these electrons from hydrogen. They pull electrons from hydrogen. But then they'll start fighting each other. And hydrogen peroxide always put in the refrige. And if there's too much heat, even if you take the peroxide, hydrogen peroxide, this is hydrogen. What's the name of this? The commercial name is peroxide. And another commercial name is called hydrogen peroxide. But what's the real name of this? Come on, guys, don't tell me. Don't let me down. What's the real name of this? You remember that? That will be in the quiz number 2, guys. What we call it? Looks like a Monday today. It looks like a real Monday. What we call this, guys? The real name, the real chemical name. Not the peroxide, not the hydrogen peroxide. What we call the real name. Chemical name. You let me down. Dihydrogen what? Dioxide. Come on, guys. Dihydrogen dioxide. Dihydrogen. 2 hydrogens and 2 oxygens. And at the end, IDE. So, okay, guys. So this is the way we can see. And if you look at the charges, hydrogen is 1, 1 minus 1 is 0. There's no charge on hydrogen. 1 minus 1 because it has 1, and 1 minus 1 is 0. This is from the periodic table. This is the chart. This is the actual one on it is 0. Oxygen is 6, correct? And you cut it like this way. 6 minus 6 is 0. This is 0. No charge on this molecule. And you can see there is no charge. And here 6, you cut it with the valence electron. Each one with its valence electron. So it's 0. No charge on this. Okay, guys? One more thing here is the something called resonance. Can I take this one out? Resonance is, we call it resonance. A resonance is migration of the double bond, migration of double bond through the molecule. Well, if I have nitrate, yes, I will give you the structure of nitrate here. Okay, guys, so nitrate will look like this one here. It's positive, it's negative, it's negative. So, and the whole thing then, nitrate is negative. So this double bond here can migrate. So I can say it can migrate then to the second one. So now it is here. Now this one here, minus 1, plus 1, minus 1. It can migrate further, and it will be here. Here is double bond. Here is minus 1, and here is minus 1. So the migration of the double bond, from one throughout the molecule called resonance. So see here, started here, then came down to the second one, then came to the third one, So this migration of the double bond, the end results of it, is higher stability. Higher what? Stability. The molecule that has resonance inside will be very, very stable. You cannot take it. Very stable. You cannot take it apart. Very, very stable. Anytime you have resonance in a molecule, that the molecule is so stable. Are you following? So that will end the story of the whole Lewis dot structure. Correct? Now, I did not see in the PowerPoint. We talked about covalent compound, this Lewis dot structure. But is there a Lewis dot structure for ionic compound? Yes or no? The answer is yes. The answer is what? Yes. Are you following me here? So let's look at this. Can I take this one out? Everybody has it? Everybody has it? Okay. Let's look at the simple one, and then we'll take another difficult one. So guys, here it is. I have for you sodium chloride. If you are asked about Lewis dot structure for this compound, well, it's nothing really mysterious about this, but we don't use that much of ionic compound. Mostly it's Lewis dot structure is heavily used for what? For the covalent compounds. But it can be used for what? For ionic compound. Well, sodium is 1A, correct? How many valence electron? Is 1. Chlorine is 7, correct? 2, 2, 2, 2, and 1. There is no sharing. There is transfer. There is what? Transfer of electrons. So we are dealing with sodium losing this electron, correct? Become positive, and the chlorine is gaining this electron here. Correct? So therefore, it will appear what? It appear 1 negative. See? That's that structure of ionic compound. Because if you look at this, sodium is losing 1, correct? It has 1 valence electron, last one, so it will be positive. And the chlorine is gaining this electron from sodium, so it will have 1 negative charge. So this is really the Lewis-Dot structure of this ionic compound. I'll give you another example, more complex, correct? Everybody has it? Everybody has this? Everybody has this? Okay, let's do another one. I have aluminum oxide. Oxide is 3 in the third. The third group will be 3. So the 3 will come from aluminum, and the 2 is given to the oxygen, because oxygen has 2 minus. So I have 2 aluminum. Aluminum, how many valence electrons? 3, correct? Aluminum has valence electrons 3, group 3. Oxygen has 6, 2, 2, 2. Then we have here and the third one is here. Now what will happen here, what is the Lewis-Dot structure of this compound? Well, let's look what will happen here. All valence electrons of aluminum will be given away. So this will go here, this will go here, correct? This will go here, and this will go here. This will go here, and this will go here. So it looks like then you have all those valence electron 3 of aluminum will be given to oxygen. So aluminum is losing all those 3, will come 3 positive, and the oxygen will have, this is 6, correct? So it's gaining, let me see. I'll put them first like this, and then we'll come. Those are the oxygens here. 6. 6. Then what will happen here? You have two aluminums, correct? Al loses 3. So 3 and 3, how many? 6. 3 and 3 positive. So at last, each one 3, we have 2. So 6 valence electrons are given to the 3 of the oxygens, correct? So here it is. This is 2 here. This is 2. 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 So because you have 2, this is 2 minus. 2, you go 2 negative, 2 minus, and the 2 minus. So number of the positive, this is Lewis-Dot number of positive charge. The sum of positive charges, how much? Is plus 6. Sum of the negative charges, this is charges here, is what? Minus 6. Minus 2, minus 2, minus 2 is minus 6. Plus 3, plus 3, plus 6. So this is the Lewis-Dot structure of the would be Al 3 plus, Al 3 plus, and oxygen is 2 minus, oxygen 2 minus, oxygen is you have 8. This is the Lewis dot structure of aluminum oxide. Okay, guys, this is the way. So we do have, that's not inside the PowerPoint. I don't know why, but it should be at least show you that's not covalent compound. They have Lewis dot structure. But what really Lewis dot structure is representing the VEs as dots. That's all the idea. Lewis dot structure, meaning representing all the VEs as dots. Okay, guys, can I take this one out? Now we'll go for something called Whisper. That's lab 5. Can I take this one out? Everybody has it? Okay, good. Now we are out of Monday, I hope. So, Whisper is VESPR. So the VE stands for valence, the E for electron, Whisper, correct? S for shell, P for pair, R for repulsion. What really says, it says that, and this we a method to determine the shape of the molecule. Method to determine shape of compound or molecule. Okay, guys, this is it's a method. It's really a method. So there are some rules for this method, but this is what it says. So it is dealing with the valence electrons, correct? And really it depends on Lewis dot structure. It depends heavily on Lewis dot structure. Okay, so what it says because the dots, those are particles, correct? Those are valence electrons. Those are negative charges. Whenever we put Lewis dot structure there, I mean the single bond, double bond, triple bond, lone pair or orphan pair or non-bonding pairs, they start those negative charges repel each other. Continuing the repulsion because they're negative, they don't attract each other, they repel each other. And the molecule goes on and off, on and off, and off until it stays to a shape that minimizes what? This repulsion. That's the whole idea of it. So Whisper is a method that really describes the repulsion of electrons till it's really comes to the rest with the stable shape, correct, in space, correct? And that's what really, the repulsion continues until you get a very stable shape that minimizes this repulsion. Okay, guys? So, and I have for you, we have two types of definition here. Oh, whoops, sorry. I'm sorry. I didn't ask if you are ready. Everybody has this? Everybody has this? Okay, good, thank you. Take it out. I'm taking this one out and then putting this here for information for you. That's in iCollege. So we have two types of shape. We have something called electron geometry, okay, versus molecular geometry. What's the difference between them? If somebody will ask you what's the difference between electron geometry versus the molecular geometry? Well, it turns out to be, for example, I have ammonia here, correct? Let me write here ammonia. Ammonia is, we have plenty of time. Ammonia looking like this. This is ammonia, guys, NH3. And always depends on those lone pairs, correct? This is ammonia here with with one set of lone pair, and three sigma, or three sigma bonding or single bonding. Sigma or single means the same thing. So this is the Lewis dot structure of the ammonia. Now, the repulsion will happen is this negative, and it has here electrons. They will repel each other. They don't attract each other. They just want to be far away from each other. Correct? And this negative will repel each other. This negative, all the time is repulsion, and the whole molecule will continue on this until those are the valence electrons here. Let me those are the two valence electrons, correct? So till you have this hydrogen. So this is the structure or the shape that's really reach, correct? Reach stability, higher stability. This is the molecular shape. The molecular shape is called trigonal pyramid. However, this trigonal pyramid, correct? Now, the trigonal pyramid does not count this those it's not counting, like they are not there. Those VE is not there. That's molecular shape. The electronic shape will tell you that's not true. Here they are. I have to have all those three, count those as well, correct? So this is tetrahedral. You see the difference? The molecular shape is not counting the lone pair. No consideration for lone pair. Or bonding, non-bonding pairs or orphan pairs. So can you see that? Those are filled, present, correct? Here, not present. So it looks like this is hydrogen here, hydrogen here. So this is nitrogen. It's like trigonal pyramid. It's a pyramid with triangle base. That's the molecular shape. That's what the molecular shape. However, the electronic shape does count for all the lone pairs. So if you look at this, we consider the single bond and the double bond and triple bond and the lone pair as one unit, or as single equal double. Let me write them maybe. That's the best. Let me write them here, guys. Single, double, triple, and lone pairs. All those are 1 unit. 1 unit, 1 unit, 1 unit. Or sometimes called 1 unit or 1 zone or 1 group. So those are all synonyms. So what's the difference now? Let me repeat myself. The difference between electronic shape and the molecular shape really deleting the influence of the lone pair, does not consider lone pairs. While the electronic one, it does really count for everything, including the lone pairs. It does count the lone pairs. That's the difference between them. And it goes by what? By the number of zoning or zones or units or groups. So how many groups we have here? How many groups do we have here? We have how many? We have 4 groups. We treat them the same thing. So we have here, let me write it again. Everybody has it? I'll write it again. How many here? Come on, guys. Can I take it out? Everybody has it? Yes? No? Okay, good. Let me take it. Now, let's look at this twice here. I'll split this one here. This is molecular shape. It's very hard to write. I mean, it's just, I'm writing like standing on a wall. It's not. I wish they have a flat iPad or something. Electronic shape. So, considers what? Considers lone pairs. We said lone pairs, non-bounding pairs, orphan pairs. That's the same thing. It's the same thing. Here, does not consider lone pairs. And if I look at this for ammonia, this is ammonia here without what? Without looking that there is lone pair there. But here I have to what? Consider what? The lone pair, and each of single bond, double bond, single equal double equal triple equal lone pair. Those are considered what? Units. Unit, group, or zones, or zone, correct? But there is nitrogen with the lone pair is considered here, correct? Here we don't consider. So the shape of the molecular shape of this will be, because we have just 3, we ignore the lone pair. So it will be like a trigonal. It's a pyramid with a triangle base, correct? Here called tetrahedral. Okay, here called tetrahedral. That's the difference. So everybody has it now. You know the difference between them. Now let's take a molecule here, and I take one out. Okay, now we know how that's not inside the eBook and not inside any textbook. That's Dr. Ataya's invention. That's my own, yeah. I mean, that's higher chemistry. We'll find it in higher chemistry once. BSEPR, and I call it whisper code. we have to know the code. What is the code is? So, well, the code is I have H2O. This is H2O, hydrogen, two hydrogens, H2O, correct? Two hydrogens, and one oxygen, correct? Now, if I consider those here, then how many zones I have? How many zones? One zone, single bond, one zone, single bond, one set of lone pair, one set. So 4 units. 4 units, zones, groups, correct? So the oxygen is a central atom, will be given a designation of A, symbol A, correct? And the hydrogen are terminals B. And each lone pair is E1 and E2, or just E. Take this one here out, it's just E. So what is the whisper code of this H2O? It turns out to be what? So PSEPR code is what? Somebody will tell me. A B2 E2. That's the code of it. Okay? Everybody's following? Everybody's following, correct? So that's EB2, EB2, E2. If I consider the electronic, how many zones we have? 4. That's tetrahedral. So electronic shape for 4 zones is always tetrahedral. But we are interested in what? We are interested in the molecular shape. Molecular shape of AB2E2 is called bent. Okay, guys? So let's look at some of the examples. I think I put for you somewhere here. Can I take this one here? Wait. Okay. Everybody has it? Everybody has it? Okay, let's look at the let's look. Can I take this one out? Everybody has it? Everybody has it? Okay, good. Good. Let's take this one out and let's look at the I might have to, I'll post it, but this is in your guys. I know we have still 2 minutes. Cool yourself down. Cool yourself down. We are not going anywhere. So cool yourself down. So here it is. We have this folder here called eBook lecture. So let's look at this. Click on this chapter 4, and then I want to show you this whisper codes. That's in iCollege, and I'll put it inside. I promise when I go home. So can you see it? Now we have, when we come back today, Monday, I think, we have still 1 minute. Cool yourself down now. You make me anxious. Everybody wants to get out. Okay, guys. Okay. I have to give up. We'll come and look at those codes and then determine the shapes. Okay, guys? Okay. Thank you. I'll stop the recording.